Welcome, everyone, and thank you for joining us at Coalesce 2021. This is our last session, and I don't know about you, but I'm feeling very excited. My name is Amala Echeverria, and I'm on the community team at DBT Labs. I'll be the host of this session, Trials and Tribulations of Incremental Models, presented by two-time Coalesce speaker Vincey Au. Vincey is currently a data analyst at Canva, where she leads the video products analytics. Fun fact, she is known for having laser eyes in PR reviews and prides herself in lifting standards. She can detect style guide deviations or anytime folks are not adhering to the style guide in the blink of an eye. On a more personal note, Vincey is a huge Python and DBT fan. DBT more, obviously. She loves petting dogs and going on picnics. And last, but definitely not least, Vincey has been an active contributor to the community Slack for almost 2 years and has been an active meetup participant at the Sydney DBT meetup since before that. Incremental models are core to DBT and are a key solution to how data teams balance the need for computationally efficient and timely data. This 30-minute talk will discuss some challenges with building incremental models at scale and how Vincey's team's approach has evolved over time in a high-growth company with over 30 third-party sources of data. Before we pass it over to Vincey, I want to share some pro tips for making the most out of this session. All chat conversation is taking place in the Coalesce-Trials-Tribulations-Models channel of DBT Slack. If you are not yet a part of the DBT Slack community, you have time to join now. Seriously, go do it. Visit getdbt.com/community and search for Coalesce Trials Tribulations Models when you arrive. We encourage you to set up Slack in your browser side by side. In Slack, you'll have a great experience if you ask questions of our speaker and other attendees, make comments, share memes, or react in the channel at any point during Vincey's session. And if you're new to the DBT community or this is your first time at Coalesce, please chime in if you like. Everyone here loves hearing from new voices. To kick us off, our chat champion, Pat Kearns, a senior analytics engineer at DBT Labs, has started a thread to have you introduce yourself, let us know where you're calling in from, and inform us on a very important preference, ice cream flavor. After the session, Vincey will be available in the Slack channel to answer questions. Let's get started. Over to you.
Hi, everyone. So my name is Vincey, and yes, up until last week, I was a data analyst at Canva. But today, what I want to talk to you about is one of the most life-changing things about DBT, incremental models, and all the trials and tribulations we have been through with them at Canva. There's a soft spot in my heart for them. So a little bit about Canva to set the context. So we're on a mission to empower the world to design. And we do this by building design software that enables ordinary people like you and me to create beautiful Facebook posts, shirts, videos, and presentations just like this one. We're a software as a service platform that operates on a freemium model, and we also operate on multiple platforms, including your web browser and mobile apps. And we've grown pretty quickly. So back in 2019, we had 15 million monthly active users. When I spoke at Coalesce this time last year, we had doubled to 30 million monthly active users, and now just 1 year later we've grown over 2x again to have 65 million monthly active users. So we're working with quite a few users, and our data has grown just as fast. So we've gone from 4 to over 80 analysts in just 3 years, and when we crunch some numbers, we have over 2 petabytes of data, and we have over 100,000 events per second generated. And more than half our data was generated in the last 6 months, which is absolutely terrifying. We use the modern data stack, so the classic combination of Snowflake, Fivetran, DBT, and Looker as our BI tool. And so, obviously, Canva has grown an incredible amount. We have more users who generate more data. We've launched more products and more features, which are also generating more data. But alongside this, we've also evolved our data maturity. So 2 years ago, our stakeholders were still asking fairly straightforward questions like, how many signups and MAUs do we have? But these days, they're asking more complex questions. what are the actions that drive a user to retain? And so these complex questions need more complex modeling. And of course, your stakeholders would like the answer to these questions yesterday. And so the real problem is that our data has grown so much that the processes we were using a year ago really don't work 4 times the amount of data. And so the real problem is that, and I think like this meme really summarizes our situation, like more data, more problems. But DBT has given many of us a lot of joy, and for me, being able to solve some of our big data problems with incremental models was one. And so today, what you're going to learn in this talk is first, some problems that you might run into when you're trying to use incremental models in high growth organizations. The second is some solutions that we have used at Canva to solve these problems. So hopefully you can learn something to take back to your job. And thirdly, we're going to discuss the trade-offs between impact and complexity of these solutions, so you can decide whether you should use these. One thing to note about everything I'm talking about today, all of the solutions I talk about gradually came up from multiple different problems over the last 2 years. So they can be a little bit distinct and they don't necessarily need to be combined together. But let's talk about incremental models. So for those of you who don't know what an incremental model is, here is a quick summary. So let's say we have a sign up completed event that we are currently materializing as a table every single day. So we load every row in this table every day. And this is what the SQL might look like. So it's a simple select star from our event. And over time, this might creep up to over an hour, which you might just suddenly decide, hey, this is a bit much. And one way we can make this faster is to materialize it incrementally. And so there are 2 main components to this. So first is to change it at the DBT config at the top of your file. So here we just have materialize as incremental. And the second is to add a piece of logic that only runs incrementally. And so for the first time you run this model, the table doesn't exist in your data warehouse. So this is incremental condition is going to return false. And so DBT is going to know to not include your incremental logic. And when you run the model, it acts like it always has, which is it's going to process the whole data set and store it into a table, which we're calling fact user signup. However, if the table already exists, and so on subsequent runs, then DBT will recognize this and it's going to include the is incremental logic inside the compiled SQL. So our logic here is pretty straightforward. All we're trying to do is to query all the new events that have come in since we last updated our fact user signup table. So we're just getting the max event time from our existing table. DBT stores this in a little temporary table, as you can tell from the name, dbt_temp. And then this is the generated query, but it merges all this new data into the existing table. And so with this, you can expect that the model now takes substantially less time to run. So let's say 5 minutes per day. And there are quite a few advantages here. So firstly, we're saving the time taken to run the model, which means fresher data quicker for your favorite stakeholder. And the second is because it's taking less compute, we're also saving money. So what's the catch? Turns out that incremental models introduce a lot of mental overhead that otherwise wouldn't occur, which leads us to our first problem. What if your data arrives late? What do you do if you have some missed events? The first thing to do is to actually size up how big of a problem this is with your data. So in our events, we get both the timestamp of the event and when we received it. And from this, we found out that for most events, we received 99% of the data within 1 day. And sometimes this was dependent on the event. So for example, we found out that mobile events have an even longer lag. But ultimately, what you're doing here is you're trying to make a trade-off between perfectly complete data and computation. And the smaller your lookback window, the less you have to compute on an incremental run. Now, once we know our lookback window, then we can add it to our logic. So here we just had a piece of SQL where it's select the max event time from our existing table and subtract this 1 day look back window. Now at Canva, we apply this to all our data. So we decided to standardize this with a macro very early on. So we created a macro, it's called get incremental start time, which takes in the table, the time column, and also the look back window. And there are a couple of things I want to point out here. So first is we define a default event-like variable in the dbt project YAML file. And this is really useful because if we introduce a change that somehow affects all models, then we can change it all in one place. So for example, if users could use the product offline, then the events might take days to send and we might want to increase this. And the second thing is that instead of actually replacing the SQL with the subquery, we actually run this query at compile time and insert the calculated date time into the SQL. And the reason why we did this was because this ended up being something like 5 times faster on some really complex models, which had a lot of subqueries and CTE. So it just helped the warehouse engine work a little bit better. And thirdly, I don't know about you, but I feel like I always experience getting this, like getting event data from like the 1970s before the product ever existed. So the third thing we did was to make sure that we don't pick up any data before Canva was launched. And this is really nice when you just want to plot all your signups over time in a downstream dashboard tool, nice and clean. And so here's how we use it. We simply call the macro at the top of the model, so on line 2 here, and then we use it in our SQL, so on line 7. And notice here that we don't need to add the is incremental condition into the model SQL itself because it's baked into the macro. And this makes the core business logic of the model easier to read. And so the macro is logically the same as doing it the long way, which is we have this subquery to select the max event time minus the look back window. But in our case, our macro actually compiles to just the date time. So this is what it looks like if you look at your data warehouse query history. Really well. We've been using this macro for about 2 years now. It's really great that it's easy to change the default look back window project wide, and it's also more efficient computing the cutoff during compile time. And something that is both a pro and a con is that it abstracts away all the logic. So it makes business logic simpler to read, but it's also more difficult for new analysts to understand what is happening. But maybe they don't really need to. So our second problem is then, what if you're combining multiple incremental models with varying source freshness? And so let's consider a scenario where we have an e-commerce website and their definition of an active user is someone who authenticated, so they signed up or they logged in or they made a purchase on the website. So now let's consider where these events come from. So our authentication event might come directly from the browser, whereas purchases might be stored into a production database first. So for example, MySQL, which is then copied into the data warehouse every day. So they come from 2 different sources that are loaded into the warehouse independently of each other. And how we would generally count active users using SQL would be to first create a table of all the active events every user fired. So in this case, we're just going to union our user authentication from a front-end event with our purchase state, purchase data from our backend system. And this is what it might look like if the table was built incrementally. So notice here that both incremental logic blocks are using the exact same piece of SQL. So we're just trying to retrieve the latest event that already exists in our table. And this latest max event time could come from either the user authentication event or purchases. And so this works really well when the sources are up to date. So here we have both tables up to date until Sunday, the 5th of December, so 5 days ago. And let's say the 6th is okay as well. And the next day, we might start to get some issues. So here we have our authentication event has the latest data, but something's gone a little wrong with loading purchases into our warehouse. The same thing happens on the 8th, and it keeps going. So also on the 9th. So let's consider what happens to our model now. So the max time stamp for the combined model is now the 9th of December. But our 1-day look back window is only going to go back between the 7th and the 8th, so where the dotted line is. And it's actually not going to go back past when purchases were last recorded. And so if purchase data suddenly catches up, then we're only going to load the data in from the dotted line, and we're going to completely miss out on loading data from the 7th of December into our table. And so we lose data and our model is incorrect. And the issue here is really that we're not taking into account every source that we're dependent on. When we're doing the incremental logic here, we're just fetching, hey, give me the latest event time from the combined events. And one really nice way to fix this is to use a min-max algorithm. So for each source of data, so authentication and purchases, we want to fetch the latest dates from that, and then we want to fetch the minimum of that. And that's the date that we build the incremental model from. So in our previous example, we got to the 9th, and then our purchase data suddenly caught up. So in this case, when we're on the 9th, purchases were last loaded 3 days ago, and because the latest purchase event dates are smaller, then we rebuild from 1 day before that, which is fine. But yes, so we rebuild from before the 5th, and so when we next load the table in, all our data will get refreshed. And so this is really nice because it works, and it works really nicely if you don't have to worry about your downstream models being incremental. So it works great if there are tables of views. The con is it's really complicated to repeat. It's actually impossible to do that once you aggregate the data even further and you lose like the differentiator between what comes from authentication and what comes from purchases. And so we patched this over a couple of times, and knowing that the fix stops at a certain layer of the warehouse. And we brought this problem to our data engineers who made this suggestion. They were like, what about if we use the warehouse load timestamp? So let me first define what the warehouse load timestamp is. So when we load data into the warehouse, we also store the exact time that it was loaded into a column called insertData. And we would consider this metadata, and this is quite different from our event time. And so here's what our previous active event table might look like. So you'll notice here that the logic is much simpler. We no longer need a look back window to do this because we simply just insert all the new events that have come in since the last time we inserted it. So the logic is so much simpler. And so pros, it works. Cons, for an analyst, it seems really silly and maybe even a little illogical to not use the event time, since that is where your fact and report tables need to use. And so internally, this kind of led to a fairly poor uptake of this solution. And the other thing is that this doesn't really solve the problem, but it does push the problem down another layer in your data warehouse models. So that actually might be good enough in a lot of cases. And so something we discussed occasionally was using freshness checks on our sources and then not running models with stale sources. Now, we haven't implemented freshness checks at Canva yet, and there are a few blockers as to why. So first is we had a lot of mixed opinions on whether failing fast was the right thing to do for our warehouse. Does it really make sense for the whole warehouse to be stale if some unimportant source is really stale? We make a lot of marketing decisions. We have a lot of marketing making decisions on millions of advertising dollars. So having fresh data is very important for that. The second thing was we needed better workflow. So we don't use an orchestration tool, and we felt like we really needed to have a proper orchestration tool to handle this. So maybe there's a small feature request is to maybe add freshness checks into DBT. But anyway, freshness checks is probably where we're heading to now, because going back to fix stale tables is a total nightmare. And we're probably now at the scale where stale but correct data is more valuable than super fresh, sometimes correct, but could potentially be wrong data. What if your incremental model still takes too long? Or what if your database runs out of memory? So it's usually pretty sensible to set a query timeout limit on your data warehouse. So this helps to stop any completely awful SQL scripts that may or may not be written by analysts from burning a lot of dollars. And so usually what we'll do next is to look into the query plan and see where the warehouse optimizer is struggling. So here's an example of a query plan from Snowflake. There's a few things worth pointing out when you look at one of these. So first is on the top right here, we can check what operation most of the time is being spent on. So in this case, the most expensive node is doing a table scan. So 57% of its time is there. And we can also check how efficient the table scan is doing by checking how much it's pruning in the sidebar. So pruning refers to when the warehouse optimizer scans the source tables, how many partitions of data it actually needs to read to execute your query. So in this case, we have about 37 million petitions and we're scanning about 40,000 of them. So it's pretty well. And so it's probably not a problem with this particular source table, with how this source table is petitioned. The other thing worth checking is the memory spillage here on the sidebar. So spillage means that the machine doing the compute doesn't have enough memory, so it might have to rewrite memory to finish the computation, which makes it a little slower. In this case, the amount of spillage, we're really just looking at remote spillage here. It's pretty small, it's like less than 5 gigs, so it's not really worth worrying about. So in this particular case, it's not really a problem with our SQL at all. Now, remember that an incremental materialization does two core steps. So first, it creates a temporary table, and then it merges this temporary table into our existing table. And it turns out that sometimes it's actually the merge step that takes a really long time. So in this case, what we have is a table that took an hour and a half to create the incremental table of, which then took an additional an hour and a half to merge into the existing table. And the reason why it takes so long really is because for each new row we want to insert, we also have to check the existing table to see if it already exists. And only then do we add it. And this process takes a really long time, especially when your existing table is like humongous. And beyond petitioning your table onto the unique key of your incremental build, there's not really that much you can do once you have that much data. Which leads me to a brand new materialization we built specifically to avoid needing to merge, and we call this insert. And all it really does is run the SQL and directly insert it into the existing table. So for those of you who are seasoned DBT users, you might be wondering how this is different from the delete and insert strategy. And there are two key differences. So first, delete and insert will still create a temporary table, and then it'll insert the results of that into the existing target table. The second thing is that delete and insert still works with the unique key, which means you can still delete data from the existing table and avoid having duplicate data. Whereas with insert, you would end up duplicating the data. The trade-off here, though, is that you don't need to search your existing data to see if it exists. And so pros and cons again, it was really great for our really big search tables. So we got to reduce the build time from something impossible to we can actually put it into our daily build because there is no need for a merge. You can't update existing records because there is no longer any merge conditions, and you're heavily relying on your logic being correct. And so we talked through a lot of incremental strategies in this talk. So first, we talked about how to handle late arriving data using the incremental materialization. And we looked at how to calculate the optimal lookback window and standardize this logic in a macro. The second thing we talked about was this tricky situation of when you have a model that relies on multiple sources, which may not be equally fresh. We learned about the min-max solution and also using the inserted metadata solution. And both of these are really just small band-aid fixes that push the problem down another layer, which may be enough. And we also said that using source freshness is probably the ideal way to handle this. And finally, when your data is just too big, we learned that you can make the trade-off of using unique key checks and instead directly insert your data into your existing table. And so when do we use these strategies? So there are 3 situations where you might want to use these. So first is when you decide your warehouse costs way too much to do what it's already doing. The second is when you're growing so much that your data is so big, you have to use this. And thirdly, even if your organization is much smaller, if your organization is comfortable with having close enough data rather than like perfectly correct data, then you might also want to use it. So we've solved a lot of problems that have come up because of incremental models, but I'm sure as we grow more and more new problems are going to come up. So it's a bit of a never-ending struggle. But hopefully with knowing some of these strategies that you can use and understanding the trade-offs, you can have a better idea on how to approach your problems.